Hello, I'm Miti Majmudar from the CRISP Lab at the University of Waterloo. Today I'll be presenting my work, Mitigator, which was done in collaboration with Ian Goldberg. Privacy policies have worked on a notice and consent paradigm. As users, we're all too familiar with clicking on a text box that says, I have read and consent to pages worth of legalese. Ordinary users cannot read pages worth of legalese every time they interact with the website. Many approaches based on natural language processing techniques, such as privacy labels, have been proposed to convey the information contained in privacy policies, such that an ordinary user can understand it. For example, Apple now requires opt-in consent from users before ad providers can track them through device identifiers and so forth for targeted ads and personalization, in a big win for privacy. Apple iOS also synthesizes privacy labels for apps. These labels allow users to tell at a glance what data items are collected or linked to their account and which ones are used to track them across apps. These labels are based on the data processing behavior of the app and of other SDKs that are linked within it, as reported by developers. However, not only can developers mistakenly forget to include data items, some companies have been known to collect users' data while mentioning it vaguely in the privacy policy. For example, earlier in the summer, Zoom was found to be sending users' location data and device identifiers to Facebook, even if the user did not have a Facebook account. Examples such as these lead us to believe that simply representing the information contained in privacy policies in different forms is not sufficient. We need to validate it by inspecting the code on the apps or on the websites. Zemek et al. And Slavin et al. Have built systems that check the compliance of smartphone apps to privacy policies. However, these systems only check the client-side code. Although other systems have been proposed to check the compliance of server-side code to access control policies or similar encodings of privacy policies, they require users to trust the server-side machines. Mitigator reduces the trusted computing base required for such a compliance check from the entire OS on the server-side machines to only a small module on them, namely a trusted hardware platform. Trusted hardware platforms address the problem of running a program on a given machine when the OS may be vulnerable or malicious, and base their trust in a small set of hardware. Here we have two programs running in containers on the same machine, with the OS being untrusted. We obtain two crucial guarantees. The state of this program, given by the content of its registers, is not accessible by the untrusted OS. Secondly, once this program is loaded into the container, the untrusted OS cannot modify it without being detected. In other words, we obtain confidentiality of the program state and integrity of the program. There are several implementations of trusted hardware platforms, such as Intel SGX, AMD SCV, ARM Trust Zone, and others. In this work, we focus on SGX based on its attestation features that I will describe shortly. However, our design can be implemented on other platforms as well. Trusted hardware containers are known as enclaves within this platform. Applications are to be split by developers into an untrusted main part and a trusted enclave part. The untrusted main part consists of system calls and calls into the enclave code, whereas the trusted part consists of code whose confidentiality or integrity needs to be preserved. The enclaves are signed by the enclave developers. The enclave measurement E1 is a hash of the enclave binary. The signer measurement S1 is a hash of the verification key corresponding to the enclave signing key. Local attestation is an important feature that we use in our design. Here we have Program 1 and Program 2 being run in different containers. We wish Program 2 to certify to Program 1 that it is running in a genuine container. Program 2 produces an attestation report that includes signatures over these signer and enclave measurements and is specifically generated for Enclave 1. Note that other enclaves or enclaves on other machines cannot verify this report. The attestation report also includes an ephemeral public key for Program 2. Program 1 then verifies this report. Local attestation involves two-way exchange of attestation reports and keys and results in a hardware-based secure channel between the enclaves. After Program 1 verifies Program 2's report, it may have its own authentication policy. These authentication policies influence the trusted computing base of the system. For example, only allowing peer enclaves with certain signer measurements requires peer enclave to be signed by some trusted party. If a client wishes to verify that a certain program is run within an SGX container on a remote machine, it runs a variation of this process known as remote attestation, which may involve communication with the trusted hardware platform manufacturer, Intel in this case. Given this background, we will now describe how the compliance check can be conducted using a trusted hardware platform. We consider a verifier that takes as input a privacy policy text and generates a model of it using NLP techniques. It also takes as input the source code of an application and conducts information flow analysis on it. Comparing the privacy policy model and the output of the information flow analysis tool, the verifier then determines whether the privacy policy is compliant with the website code or not. Slavin et al. And Zemek et al. Have built such systems for checking the compliance of client-side code of smartphone apps to their privacy policies. We imagine a similar system deployed on the backend server machines. Of course, in our threat model, we cannot simply trust these machines, and so we essentially run this verifier within a trusted hardware platform. The website code itself is also run within an enclave that is known as the target enclave. In case of a successful compliance check, the verifier enclave signs over the specifications for the target enclave. The target and verifier enclaves are run within a library OS, Graphene SGX, which we will describe later. This stage is known as the verification stage. We assume for our security analysis that this verifier program is sound, but not complete. In other words, it will only produce a signature over the target if the target is compliant with the privacy policy, and only such compliant target programs can be run. However, real-world verifiers may not be sound, and thus they may inadvertently allow non-compliant target enclaves to be run. Let's start with looking at the components of our design. I've described the verifier and target enclaves. Apart from the user's client, which is a browser extension, we also have a lightweight decryptor enclave. The verifier and decryptor enclaves are expected to be open sourced so that experts can review the code of these components as well as for the client to authenticate the website as being compliant. However, the target enclave does not need to be open source and may contain proprietary code. Not all parts of our system are online at all times. As we already saw, in the verification stage, only the verifier enclave is online, and it creates a signed target enclave. We have two other stages, namely the deployment and runtime stages. We start with the verifier and the decryptor in the first part of the deployment stage. The verifier conducts local attestation with the decryptor to establish the secure yellow channel. It then sends two types of information to the decryptor over this channel. First, it sends the compliant target signer measurement to allow the decryptor to authenticate the target. It also sends information related to the compliance check. The verifier does not need to be online anymore. In the second part of the deployment stage, the target conducts local attestation with the decryptor to form a secure channel with it. During this attestation, the decryptor authenticates the target using its expected signer measurement that it obtained from the verifier. Over the secure channel, the decryptor then forwards two types of authenticated information to the target enclave, both of which are later on forwarded to the client. The decryptor sends the verifier's enclave measurement and also sends the compliance check information that it obtained from the verifier. We now move on to the runtime interactions in Mitigator, which involve the client. The client is required to conduct one remote attestation with the decryptor enclave behind every Mitigator supporting website. As the decryptor is open sourced, the client can compute its expected enclave measurement. The client authenticates the decryptor based on this enclave measurement. This remote attestation needs to be conducted the first time the user visits the website and every time the decryptor code changes. It is thus important that the decryptor code base is small and does not change frequently. The decryptor sends its verification key over the secure channel with the client that is formed through the attestation. The target will typically offer an interface for the client to communicate with the decryptor in order to conduct this attestation. After conducting this attestation, the client sends an HTTPS request to the target website as usual. The target website responds back with the authenticated information that it obtained from the decryptor in the deployment stage, apart from the usual HTML pages. That is, the target sends the verifier's enclave measurement as well as the compliance check information. The client verifies the integrity of this information using the decryptor's verification key that it obtained during remote attestation. It computes a list of expected enclave measurements for the open-sourced verifiers and checks that the verifier's enclave measurement is within this list. It also ensures that the web page forms displayed to the user are indeed the ones checked by the verifier by using the compliance check information. The client then encrypts the user's personally identifiable information to the decryptor enclave and sends the ciphertext to the target. The target forwards this encrypted PII along the secure channel with the decryptor. That is, it encrypts it again to the decryptor. The decryptor removes two layers of encryption, one from the target and one from the client, and then re-encrypts the PII back to the target. The target website code has been checked by the verifier to only process this PII in ways that are compliant with the privacy policy. In summary, in the verification stage, a signed target enclave is output by the verifier. In the deployment stage, the decryptor authenticates the verifier and target enclaves and forms secure channels with them. The decryptor sends authenticated information to the target enclave. In the runtime stage, the client needs to conduct remote attestation with the decryptor enclave behind each Mitigator supporting website the first time the user visits it, until the decryptor codebase changes. Importantly, the client does not need to repeat these remote attestations every time the website code, that is the target, changes or the verifier code changes. Every time the user visits the website, the client ensures that a valid verifier enclave has checked the compliance of the target website, and in this case, it sends encrypted personally identifiable information of the user to the decryptor. The decryptor only hands over the client's plaintext PII to a signed and verified target website enclave. Our design has two subtleties that I would like to highlight. Our enclave authentication policies do not require the verifier or decryptor enclaves to be signed by a trusted party. In fact, they are expected to be signed by the company that hosts the website. We simply require these enclaves to be open-sourced for the client to authenticate them based on their enclave measurements, that is, hashes of their code. Second, many website providers may not want to reveal the frequency of updates to the website as long as it is still compliant with the privacy policy. In our design, the client does not learn the target's measurements, including the enclave measurement, and thus cannot infer this frequency of updates. We include an informal security analysis of our design within our paper. We now provide an overview of the implementation of our prototype. Our client is a Firefox extension. Our decryptor is built within the native SGX SDK setup, so it consists of an untrusted application that communicates with the verifier and target, and a trusted application that performs cryptography operations. We need to run other heavyweight applications, that is a static analysis tool and a website, within the verifier and the target respectively. For our prototype, we choose to run these applications without partitioning them using the Graphene SGX library OS. Graphene SGX seamlessly supports system calls within unmodified applications, allowing them to run within an SGX enclave. Our target website includes a PHP form page that simply echoes back the supplied fields. The target enclave consists of an Apache web server, including the PHP source code files and a PHP extension to perform attestation. The server, PHP engine, and extension are all run within a Graphene SGX enclave. We have a simplified Verify prototype as we focused on implementing the cryptography for the deployment and runtime stages for all enclaves. Our Verify prototype uses the Pixie PHP static analysis tool to analyze the website PHP source code files within Graphene SGX. We manually tweak the configuration options for our static analysis tool to emulate a privacy policy model. Our main challenges for the deployment and runtime stages included developing the decryptor module as well as incorporating local attestation within Graphene SGX so that the target and verifier enclaves can form a secure channel with the decryptor. We evaluate our system for the latency overhead of the server-side components as clients send larger form field data. These larger form fields could correspond to images or videos. The total server-side latency of Mitigator as measured from a remote client is shown in blue. The latency of an Apache server run within Graphene SGX is shown in orange, and the latency of a native Apache server is in green. For our simple website, Mitigator's total latency for generating the return HTML page, which consists of the plaintext PII, is shown in red. This red plot includes the latencies for the decryptor and target enclave PHP extension. It is evident that the total latency for Mitigator is dominated by the network latency, going by the gap between the blue and the red lines. The overall overhead of Mitigator is in the order of 1 milliseconds in comparison to the Apache server in Graphene, even when longer form fields are sent. Note that the Graphene SGX and native Apache servers do not provide the privacy guarantees that Mitigator does. Other systems based on trusted hardware platforms have been proposed for privacy policy compliance related tasks, such as Riverbed, SGX Use Privacy, Secure Data Capsules, and Safekeeper. These systems may have slightly different threat models and goals. Specifically, they have one or more of the following drawbacks. They may require a larger trusted computing base than Mitigator. They may require dynamic analysis tools. Applications may fail or abort at runtime, resulting in a degraded user experience. They do not mediate the system end-to-end, or do not provide a guarantee to users, or do not support general operations on users' data. In summary, we address the problem of ensuring that the server-side code of a website is compliant with the statements in its privacy policy. Our system, Mitigator, provides a verifiable guarantee to a user that the personal data that they submit to a website can only be processed by code that has been verified to be compliant with the website's privacy policy. We provide a proof of concept implementation of our system using Intel SGX at the codebase link in the slide. Thank you for listening to my talk, and I'll be happy to answer any questions that you may have.